Here's another problem. We're going to calculate using the relationship of velocity, the speed of sound, lambda, the wavelength, and a specific frequency. A sound wave has a frequency of 700 hertz in air and a wavelength of 0.5 of a meter. What is the temperature of the air? So we're going to use a couple different relationships. So the speed of the sound wave then can be calculated by manipulating our relationship where velocity is equal to the wavelength lambda times the frequency. So 0.5 meter times 700 hertz in this case gives us 3.5 times 10 squared meters per second as the sound speed. So we know that velocity in air can be calculated with 3.35 meters per second times the square root of the temperature divided by 273 Kelvin. So we move our terms around so that we can get our value freed up here, in this case the temperature, because that's what they're asking for. So we're going to manipulate this first relationship so that we have velocity then by 331 meters per second is equal to temperature divided by 273 Kelvin, of which we take the square root. So now if we take the square of both sides to free up and remove that square root radical, we end up with velocity over 331 meters per second squared is equal to the temperature, which we're trying to solve for, divided by 273 Kelvin. So now we have it as such that we can multiply both sides by 273 Kelvin. We get the temperature equal to 273 Kelvin times the square root, or times the square of the velocity divided by 331 meters per second. We calculated the velocity in the first step, 3.5 times 10 squared meters per second, so we can insert that for our velocity for the specific wavelength and frequency, and we end up with 305 Kelvin. We do our conversion from Kelvin to centigrade, 32 degrees centigrade or Celsius.